confidence intervals for proportions are always going to use the z distribution. So that's the good news. We already know if it's going to be one of the proportion problems that we're going to use the z distribution. In terms of her formula sheet, when we're doing the confidence intervals for a proportion, we come on over and we've got a fun looking formula that I'll write down separately. And there's a condition that we have to check. We have to make sure that n times p and n times 1 minus p are at least 10 in order for it to be appropriate for us to use this particular formula. So in order for us to be able to check that, we got to know what n is, we got to know what p is and all that. And it can be a little bit trickier in the proportion problems. Let me zoom in a little so we can see the words. So let's take a look at one and then we'll kind of talk through it. A survey of 200 high school students found that 124 said history was their favorite class. Construct a 95% confidence interval for the true proportion of students who like history the best. Okay, so we could look at that. We could say 124 out of 200, that's more than 50%, right? To figure out exactly what it is, what would you have to do? To get a proportion. Right, so you'll take the 124 and you'll divide it by the 200 to come up with what the actual sample proportion is. Okay, so if we take 124 and we divide it by 200, that's going to be what we call the p hat in this problem. It's the proportion, and when we put the little hat over it, we're saying it's for this particular sample. So the p hat is going to be the 124 students who said they like history best out of the 200 students total. And usually we like to turn this into a decimal when we're doing these types of problems. We don't have to, but it lets us come up with percents at the end. So 124 divided by 200 is going to come out to be 62%, which as a decimal is 0.62. So they only surveyed 200 high school students. If they surveyed all the high school students, we might come up with a different percentage. So what they're saying is, we'd like to come up with a confidence interval that would be for high school students in general, for full population of high school students, how many of them would say history was their favorite subject? So not just from our sample, but from the true population. We can't come up with the exact answer, but we can be 95% confident if we follow our procedure for setting up the confidence interval. Okay, so this p hat here is going to be used in the formula that she has set up for us. I'm going to write down the formula for the confidence interval for a proportion. It's p hat plus or minus z alpha divided by 2 times the square root of p hat times 1 minus the p hat, all divided by n. And this would be on her formula sheet, so it wouldn't be a thing you need to memorize. But we would know that we were using this formula instead of the one where we are plugging in a mean, because in this particular problem, we're not talking about an average. We're not talking about specifically a mean. We're talking about a proportion. So when that happens, we always use the z table. So this one's nice. We don't have to worry about a z versus a t. It's always going to be a z. The other parts in here, we have a particular requirement. We need n times p to be greater than or equal to 10, and we need n times 1 minus p to also be greater than or equal to 10 for us to be able to move forward. Okay. The P is the P hat. So we already have that number. What's my N?
Is the P in the NP greater than or equal to 10, the P hat?
The P that's in this formula is going to be your P hat. Yes. Yeah, for our sample, our N is 200. Okay, so what we have to check is that 200 times 0.62 is at least 10. Okay, so 0.62 times 200 comes out to be 124. So we're okay there. But I also have to check that N times 1 minus P is greater than 10. So 1 minus 0.62 is 0.38. And we're going to multiply that by our 200 as well. That came out to be 76. They're both at least 10, so we're good to go. So in this case, we met those requirements. We have the P hat, so we can do everything in this formula except for the Z alpha over 2 at the moment. The Z alpha over 2 is coming from the fact that this said this was a 95% confidence interval. So we're going to get our Z table. And we want to find where 0.9500 is in the middle of the table. The negative side, too small. We got to go to the positive side. If we need 95%, 0.950 is actually one of the ones that has the cute little star on it on the table that she gave us. Or you may have noticed down at the bottom, there's this cute little box down here that says there's some really common numbers that we use. When we want a 95% confidence interval, the critical value is 1.96, which if I go back to where this little star was on the table, if I came across for the 95% confidence interval, the reason that it's not going to be the 0.95 number is actually because I skipped a step. Do we remember what step Jen skipped? If we have a 95% confidence interval, how much is in each tail? Yeah, 2.5% is in each tail. So I actually don't want to go hunt for the 0.95 number. You are, yeah, either you are looking for the, if you move this backward, you're looking for the 0.025 number, or if you add the 2.5 to the 95, that's 97.5. So we would do 0.975. That's the number we're looking for. And so if I go find that number, .975, if I come across, that's 1.9. And if you go straight up, that's 6. 1.96 was down at the bottom of this table for the 95% confidence interval. It gave us a little cheat corner on the table. The cheat corner on the table says for a 95% confidence interval, we want to use 1.96. So 2 ways we could have done this, either directly from the table or find the little cheat corner. So our Z alpha over 2 is going to be 1.96. So we're ready to plug stuff in. My P hat is the 0.62 plus or minus. The Z alpha over 2 is the 1.96. And then square root of our P hat we said was 0.62. And then 1 minus the P hat is going to be the 0.38. And our N was 200. So if I do this calculation right here with this square root and then multiply it by 1.96, that gives us our error bound measure. So I have 0.62 plus or minus our error bound measure. So I'm going to go find that. So I have 0.62 times 1 minus 0.62 is 0.38. And I'm going to divide that by the 200. And we're multiplying that by 1.96. So my error bound measure is 0.00231 if I round it. And so to do your confidence interval, one of the times we're going to add that number, one of the times we're going to subtract that number. So we always put the smaller number over on the left-hand side. So the first time I'm going to do 0.62 minus that number. Which gives me 0.618 if I round it. And the second time I'm going to add that number. So I'm going to do 0.62 plus 0.00231. Which gives me 0.622 if I round it. I'm just going to double check and make sure that I put all that in right. I'm feeling weird about that number. 0.62. I did not do the square root. I knew something was wrong. All right. Sorry about that. It's too much. Okay. The formula was right. I just didn't put this into the calculator correctly. Okay. 0.62 times 0.38 divided by 200. Square root that. Now multiply that number times 1.96. Okay. So that gives us 0.0673 there as my error bound measure. Okay. Now we're better. Okay. 0.62 minus 0.0673 equals, there we go. 0.553 if I round it. And then 0.62 plus 0.0673, which is 0.687 if I round it. Okay, that's better. Bring that down a bit so we can read the words. That's my confidence interval, and the confidence interval we're going to want to write in words to explain what the heck we're getting here. So it said that we want to find the 95% confidence interval for the true proportion of students who like history best. So we are going to say we are 95% confident that the true proportion of students whose favorite class is history is between 55.3%
and 68.7%.
That's very.
You think so? What subject do you think they'd like best?
Yeah.
Yeah.
I was just hoping maybe, you explain how you like figured out that n times p is greater than or equal to 10, and also n times 1 minus p is greater or equal to 10.
Yes, what's our n in the problem?
The n is, 200.
200. The p is always gonna be the p hat when we do these problems. So you're literally gonna take 0.62 and multiply it by 200, and you're just checking to make sure that's bigger than 10. It was 124, we're good to go. Then if we take 1 minus p, that's gonna be 1 minus 0.62, that's 0.38. And we're gonna multiply that by 200, and we're just checking to make sure that's bigger than 10. 76, we're good to go. Yeah. Yeah, fortunately, it's usually a pretty quick check. Good question, yes.
For the C's, could we write that? It's like P is greater than, or P hat is greater than 0.553 and less than 0.687. Like I know like some of the other ones that we do the confidence intervals for, we like write like.
When you write the greater than or less than signs instead of the.
Yeah, instead of the parentheses.
Yeah, so what this is basically saying is that this is the smallest value and this is the biggest value. So what you're doing is you're putting that p hat in the middle. And whatever the smallest value is gonna go over on this side, so 0. Or I guess if you wanted to turn it back into a percentage, we could do that, we would say 55.3. So p hat has to be bigger than that, so you'd put greater than that direction. But p hat has to be smaller than this bigger number, 68.7%. So that's another way that you could write it. Yeah. Yes. Other questions? So the formula is going to stay the same whenever you're doing proportion problems. What changes is usually that Z value in there, depending on if they said it's a 95% confidence interval, or like the next one, a 90% confidence interval. So we're gonna use the same formula again. We're gonna do a 90% confidence interval. If you look at your Z table, a 90% confidence interval, if you go down to your little cheat corner, 90% confidence interval, you're gonna use the Z value of 1.645. In this problem, it says, out of a random sample of 150 light bulbs from a factory, 12 were found to be defective. Construct a 90% confidence interval for the proportion of defective light bulbs produced by the factory. So they want to know the true proportion for all the light bulbs, not just for the sample. But in order to do that, we only have the sample that we can work from. So you're going to find your p hat. What do I have to do to find the p hat? Yes. So our p hat is going to be 12 over the n, which is 150. Okay, 12 over 150 gives us 0.08. So before we move on, we got to double check that n times p is greater than or equal to 10, and that n times 1 minus p is also greater than or equal to 10. So my P is 0.08. I'm going to multiply that by our 150. And I got 12. So we barely made it. We needed to be greater than or equal to 10. It was 12. So we're good. That one's fine. We also have to check that n times 1 minus p is greater than or equal to 10. I have a feeling that that will be a bigger number. 1 minus 0.08 comes out to be 0.92. And we're multiplying that by the n, which is 150, and you get 138. We're definitely okay for that one. So we met our conditions. Now we just got to plug things into our formula. So we're going to put down our p hat plus or minus the z alpha over 2 times the square root of p hat times 1 minus p hat, all divided by n. And we have all those numbers. Yes.
Oh, what happens if one of those two are not over 10?
And you don't get to do this.
Oh.
So our conditions are not met. Now, does that mean that like most people wouldn't do the problem? They'd probably still go ahead and then they'd write like a little asterisk off to the sides, but we didn't meet the minimum conditions. She's probably not going to give you a problem like that, but she might ask you maybe like a multiple choice question would be like, here's the following problem. What might be an issue here? And you would say, oh, n times p is not greater than or equal to 10. Like that could be like a multiple choice type of question, but she's not probably going to give you a problem where she asks you to go through and solve it like it's a trick question and then be like, wait, we shouldn't have solved it. It just means that the accuracy of our answer kind of gets called into question if we don't meet those minimum conditions. But we didn't have that problem for this one, so we're good to move forward. Our p hat was 0.08 plus or minus. The z alpha over 2 for a 90% confidence interval was the 1.645. And then we're going to go ahead and plug in our p hat times our 1 minus p hat, which was 0.92. And we're dividing by our n, which is 150. So we'll see if Jen can remember to hit the square root button this time. Okay. 0.08 times 0.92 divided by 150. That number needs to go under the square root. And I'm going to multiply it by 1.645. So I have 0.08 plus or minus my error bound measure, which came out to be 0.0364 if I round it. And then one of the times I'm going to subtract the number, one of the times I'm going to add the number. So I'm going to subtract first. So I got 0.0436 if I round it. And then when I add the number, I got 0.116. So in terms of actual like words here, we were asking to construct a 90% confidence interval for the proportion of defective light bulbs produced by the factory. So not just the sample, but all the light bulbs in the factory. We are 90% confident that the true proportion of defective light bulbs is between 4.4% and 11.6%. I think you have a homework problem that needs you to do this.
Half the going to be it's calculating half of when I got it right.
Right. So the next thing that usually pops up is the hypothesis testing stuff, which I sort of started in our last class and then I abandoned. I'm coming back to it now. So hypothesis testing. It's like we're practically there when we're doing the confidence intervals, but we just have this little added thing of us starting with a null hypothesis and then we're testing whether or not we have enough evidence to reject our null hypothesis, or if we can't reject a null hypothesis. We can't actually prove the hypothesis one way or another, but we look for evidence and we say we have enough evidence to suggest that we should be thinking the alternative hypothesis is true, or do we not? Okay. I lost my first page. Let's see if I can find it. There's my first page. I found it. Okay. All right. Using the normal distribution, so I'm telling you here, this is like normally you don't get it told to you at the top of the problem that it's going to be one where you're using the Z distribution. But we'll start with telling you we have a known population standard deviation. Okay. If I know the population standard deviation, then she had given you a cute little chart. And it helps you figure out if you should be using the Z distribution or the T distribution. So for this problem, we have a known one. So we go this direction. Yes. Okay. So then it matters in the problem what our N turns out to be. Okay. So let's read the rest of this and we'll see if I can figure out if I am going to use my Z distribution. A company produces energy drinks that are advertised to contain 16 fluid ounces per can. The quality control team randomly selects 40 cans and finds that the sample mean is 15.8 fluid ounces. The population standard deviation is 0.5 fluid ounces. So that's our sigma. They told us that we had a known sigma. There it is. At a 0.05 significance level, that's the same thing as saying a 95% confidence level if we were doing a confidence interval. But a 0.05 significance level is just telling you the alpha straight out. At a 0.05 significance level, test whether the average volume of energy drinks is less than 16 ounces. Significance level is your alpha. Yes. So what's our N in this problem? N is 40. Good. Okay, so with that information, I'm over here. They gave us the sigma. So we're over on this side. And then it says, is it normally distributed
turns out, since it doesn't like, they didn't tell us that it was normally distributed. If they said yes, we would immediately go down to the Z. But if we said we don't know, we could come to the no direction. Is n greater than 30? And we got a 40. So yes, we're still going to use the Z distribution on this one. So we're going to use Z. And in terms of how we're going to do this problem, the other pieces of information that we got that our alpha is 0.05. And they gave us a sample mean. A sample mean is an X bar. They said the X bar was 15.8 fluid ounces. But they gave us a population standard deviation. So not an S, they gave us a sigma. They said that was 0.5 fluid ounces. So I'm going to go back to the formula sheet that she'll give you for the test. And the formula sheet, when we have a known sigma, so that's this one right up here, then we're going to be using this test statistic to do our hypothesis test. So the hypothesis test, we got a null hypothesis written here for us that the mu is equal to mu naught. What does that mean? That means that whatever they're telling you the amount is that we believe to be true. So that the company says we believe it has 16 fluid ounces per can, that's going to be our mu naught. So we're going to set up a null hypothesis. Oh yeah.
I'm just how to use that formula.
Yep. So first deal, we're talking about means. So it's not going to be the population one. So I know it's not there, and it's not, we don't have two different populations. So we're not using anything further down on the sheet. So it's got to be one of these two. Top two both say population mean mu. And you're like, okay, which one? Well, because over in the last column, she's got written out use when sigma is known or sigma is unknown. We got the sigma in this problem, so we're on that top formula. Okay, so that's going to be important when you're taking your test to see what she gave you. And so that's why I always write off to the side what's all the stuff we got, because then I can be like, do we? Yes, we have the sigma. That one's there. So we're on that first formula. Yes. Okay.
Like are looking for specifically to know which one to look for.
Like
If we're looking for the X bar, how do we know that's the X bar? That makes sense.
Oh yeah. So in the words that she's giving you, okay? So first thing when I'm reading the first sentence, a company produces energy drinks that are advertised to contain 16 fluid ounces per can. We're about to hit that as our null hypothesis. Remember when I was talking about null hypothesis versus the alternative hypothesis, the null hypothesis is boring. It's the status quo. So if energy drink company says they're 16 ounces per can, and you're doing a test to check if they're 16 ounces per can, what would be boring is if it's exactly what they told you it is. Like, yeah, they're 16 ounces per can. That's the null hypothesis. There's 16 ounces per can, and there's really not. Right? And we could do tests different directions. We could do tests to say, is it just not 16 ounces per can, but it could be higher. Maybe they're actually being nice and they're giving you 17 ounces and only charging you for 16 ounces. Or maybe they're being mean and they're giving you less than 16 ounces, but they're charging you for 16 ounces. That would be a two-tail test. If you don't care which direction, that's two-tail. A one-tail test would mean I'm checking to see, are they cheating us out of money? Then you would want to test to see if the alternative hypothesis is that there's actually less than 16 ounces per can. Or you're wanting to test to see if they're a really generous company and you're only testing to see if they gave you more than 16 ounces per can. That would also be a one-tail test. But usually out in the land of statistics,
we tend to kind of be like, I don't actually know. Like, I'm gonna test if it's 16 ounces, but it could be higher, it could be lower. I don't really know. We usually keep it open and we do a two-tail test because then we're like, well, we can figure out if there's more or there's less. You know, that way we can find out either way. Okay. So in this case,
The way that they wrote this one, I didn't write this problem. So let's see what kind of test they wrote, because somebody else wrote the hypothesis.
they wrote that the null hypothesis is that the mu is greater than or equal to 16 ounces. And they wrote that the alternative hypothesis is that the mu is less than 16 ounces. Did they write a one-tail or a two-tail test? If the alternative hypothesis turns out to be true, this one, if it turns out to be true, then you're saying that the mean amount of energy drink in the can is less than 16 ounces and that they're cheating you. So what kind of test did they do? Just one. Two-tail test would mean that they put an equal sign up here and they put a not equal to sign here, and they didn't care which direction. The way that people wrote this particular hypothesis, they wrote a one-tail test. I personally, if I were a researcher and I didn't know if I was checking to see if the company was cheating us, and I was just saying, oh, well, maybe the company's generous, I don't know, I'd write a two-tail test. But they wrote a one-tail test. They're checking to see, are they lying to you, and they're charging you for more than you're actually paying for. Okay? So, because of how this one was written, we are going to change up what we do with that alpha value. If it's a two-tail test, you're going to cut that alpha in half. And you're going to check the 0.025 on each side. But if it's a one-tail test, all that alpha is going to go in that one tail. So because this is a one-tail test,
The alpha that we're going to use is going to be all checking on just one side. So we're going to keep the alpha at that level and not cut it in half. So when I go to write her formula down, I'm going to write the formula so that my z is not an alpha over 2, it's just a z. So my z is equal to the x bar minus the mu naught divided by sigma over the square root of n. Yes, that is coming from the formula sheet that she gave you. Okay. Now, she's writing z sub s as our test statistic. Sometimes this z is going to be an alpha over 2, and sometimes it's just going to be an alpha. The reason we're going to just leave it as a z and not a z alpha over 2 is because this is a one-tail test. So I'm going to write one-tail test. Actually, I'm going to write it over here. Because it's a one-tail test, we're not going to do z alpha over 2. Just the z, yes.
Also, looking at the T table and know the significance level is also kind of matches. Could you like use it to tell if it's one tail or two tail, or is that not always good?
On your T table?
Yeah, just because like seeing the was it the significance level
Mm-hmm.
matches that was.
If you were using the T table and the T table says one tail and two tail at the top, then they're making it easy on you. If we know that we're just going to do a one tail test, then we're going to stay on the one tail line. If we're going to do a two tail test, we're going to stay on the two tail line. So the fact that we are doing a one tail test for this one, we're going to leave the alpha at 0.05. I'm not going to cut it in half. So I would, if I were using the T table, we're not for this one. If we were using the T table, then I'm going to stay in the one tail test and I would just go to the 0.05 right here. I wouldn't cut it in half. If it were a two tail test, So if instead of putting a greater than or equal to sign here, they just put an equal to sign, and instead of putting a less than sign here, they put a not equal to sign, then when I saw my alpha, I'd have to cut that alpha in half. So we would make it 0.025. So then you would have on your two-tail test, if you were, instead of doing the 0.05, you're going to be on your two-tail test coming over to the 0.025, which on this one, sorry, one tail for it would be 0.025 and your two tail together would be the 0.05. Yeah.
Got it.
So we would cut it in half. But we're on the Z table. And you're going to actually get your Z score by plugging in what they gave us here. So they gave us the X bar was 15.8. The mu naught is the mu that the company is telling you. The company said it was 16 ounces. So we're plugging in 16 for that. So I could write that off to the side here as something else they gave us. The mu naught was 16. Okay. And they told us that our N was 40. So we're going to divide by the square root of 40. So we got negative. So what I'm going to do is draw myself a little sketch now of a distribution. And remember, a Z score of 0 would be right here. So negative 2.53 is going to be over on this side. So I'm going to go ahead and put negative 2.53 like here. And this is a one-tail test. So what we want to know is we want to know what's the area in this one tail over here. The good news is that a Z table always gives us the area from the left up to that point. So we're just looking for what's exactly in the table at negative 2.53. We don't have to do any work. There's no 1 minus anything happening. So I'm going to go find negative 2.53 on my Z table. Negative 2.5. I'm coming across to 3. I got 0.0057. Okay. Here's the piece that makes this a hypothesis test. After you have your Z-score, you use the Z-score to go find your p-value. And we always compare the p-value to our alpha. This problem, the significance level was 0.05. It's our alpha. And here's the rule. The p-value tells you how likely something is to occur. This is 0.0057, and you're comparing it to 0.05. So there were 2 zeros here. There's only 1 0 here. If your p-value is smaller than the alpha level, then we have evidence that says we can reject the null hypothesis. So you're looking for an unusual p-value.
An unusual p-value is a p-value that's smaller than your alpha. I know they look similar because they have a 5 in it, but this one only has 1 0 in front. This one has 2 zeros in front. This is way smaller. Your p-value here is way smaller than that alpha. So because the p-value is smaller than the alpha, we reject the null hypothesis. Our null hypothesis was that the company was giving us at least 16 ounces in the can, but we're rejecting that. So we're saying there is evidence to suggest that the true mean amount of energy drink in the can is less than 16 ounces. Or in other words, there's evidence to suggest they're cheating you out of soda. So I'm going to write, there is sufficient evidence to conclude that the true mean volume of energy drinks is less than 16 ounces. So that was a lot. If you haven't got to the hypothesis testing with her yet, I just explained this to you for the first time, so it's good. She'll be explaining it to you a second time. When you go through and you're doing a hypothesis test, they need to give you a significance level. They'll either say you're going to test it at a 95% confidence level, and you got to know that's a 5% significance level, or they'll say the significance level to you, or they'll say alpha is this. If they say alpha is this, they gave you the significance level. Okay. What you're always doing when you're doing hypothesis testing problems is you're going to go find a p-value, and then you always compare the p-value to the alpha. You want the p-value to be smaller than the alpha for you to get to reject the null hypothesis. So when people are like, what do you mean you want it to be? Well, what I'm talking about is if you're really a researcher, you want interesting information. So we're like excited if we get to reject the null hypothesis. So when I say that's what we want to do, I don't mean that like that's good news. Like they're lying to us, it's bad news. But like I want to be able to say something interesting. And so what's interesting is that we have enough evidence to conclude that they're lying to us. So I'm interested. So the reason we have enough evidence is that that p-value is smaller than the alpha. You're always looking for the p-value to be smaller than the alpha. Like if you have to write yourself big things in stars, you want the p-value to be smaller than the alpha so you can reject the null hypothesis. Then when we're doing that, we use a line at the end where we say, there is sufficient evidence to conclude, and the thing that we're concluding is always the alternative hypothesis. So when you were like, how do you know to write that next part, Jen? Well, once I said I was rejecting the null hypothesis, the null hypothesis was this one, so we're rejecting that one. So that means that I'm concluding that there's sufficient evidence to suggest that this one is true. This one says that the mean is less than 16 ounces. So what I wrote was, there is sufficient evidence to conclude that the true mean volume of energy drinks is less than 16 ounces. I'm writing the alternative hypothesis down. If value is bigger than alpha, we fail to reject the null hypothesis. And what I would write is there is not sufficient evidence to conclude that the true mean volume is less than 16 ounces. But in this case, there was. Yes.
I'm sorry, can you repeat what you said? If the p-value is bigger than the alpha, that would be what?
If the p-value is bigger than the alpha, we fail to reject the null hypothesis.
Will we ever get something where the p value is the same?
Good question. If you did in the real world, so like in the real world, yes, it could be that you would end up getting a result that was equal to your p-value, and you would have to make a call as the researcher to be like, do I think that that is enough evidence to conclude that, or do I think that's right on the border? Usually you're choosing a p-value that's sufficiently small that if you got exactly that p-value, you'd still be like, I still feel like I have something interesting to say.
Okay.
The p-value is up to the researcher. So the particular researcher here decided that they wanted a 5% alpha, but if they wanted to be even more significant, they would have chosen a 99% confidence level, or they would have chosen a 1% significance if they wanted to be even more sure. 5% is usually, a 0.05 is like the standard. So like if in a problem they don't actually tell you a significance level, we pretty much always assume it's 0.05. They don't tell you one, we assume it's 0.05.
These are really weird the first time you see them. So if you're like, I have no idea what just happened, Jen, that's normal. Takes a few for you to be like, okay.
So I'm hoping when she's going over them, it feels a little bit more like, okay, I've seen one of these now. Yeah.
Explain one more time when we go to p value.
So whenever we've got problems like these, we're taking the information that they gave us and using her formula sheet, you're going to go find your test statistic. So for this one, because we had that the sigma was known, the test statistic column told us we were going to go find a z. So we did her z formula, and what popped out was negative 2.53. The z is here. And when I make you a picture, the area under the curve is the same thing as a p-value. So we got the z was negative 2.53, which tells us since this is a one-tail test, I need that area under the curve. So that meant that I was looking on the negative z part for the negative 2.53. And we came across, and that 0.0057 is telling us that's the area under the curve right there. The area under the curve is always the p. So we got the P by using the Z. Lots of letters of the alphabet involved, huh? What is a p-value? It's a probability. It's a percentile. It's a percentage. It's all the things that we did before when you use the Z table and you had that middle piece that you were looking for. And we said, oh, well, if they said that you want the 95th percentile, you went to the middle of the thing. The p-value is that same thing, that middle of the table part. Yes.
So based off of the problem and the instructions they give us on the problem, how did you know that? Is it because of the significance level? That's why you figured out that we needed to go to the middle of the table? Because they gave us the significance?
Oh, I knew that we needed to go to the middle of the table because our test statistic was a Z. We use that Z score. When you use a Z score, what you get is a p-value.
And we use the C because that's what was given to us.
Because that was